So yeah, in this situation, we would distribute the sine of x times both. The cosine of x and 2. So not the opposite, but something to think about that looks a little bit like that, but is totally different, is something that looks like this. Sine of x plus 45 degrees. So huge difference between these two expressions, because this tells us to distribute. We've got the sine of an angle, and we're multiplying it by another trig function, and then we're multiplying it by just a number. Versus here, we've got two angles that are being added together, and then we're going to take the sine of those two angles. So we have to think a little bit differently about how we're going to handle that, and that's when we're going to use our sum and difference formulas. I'm going to call them identities because that's what they are. You can think of them as formulas if you'd like, but we cannot distribute here. So a lot of people think, oh, I'll just do the sine of x and the sine of 45. Well, that's not what's happening here. We'd have to find out what this angle is first and then take the sine of it. Okay, so that's what these formulas are going to be used for. So let's take a moment and just talk about what we're seeing when we look at those formulas. So your sum and difference identities, on your reference sheet, there are 6 of them. Each one of them has a trig function and either a sum of two angles or the difference of two angles. The key to this is knowing which one to use at each kind of step along the way. So let's just practice a little bit with that. So let's say I have, let me get my example up here, the cosine of 90 minus x. And I want to show that that is equal to the sine of x. I am so sorry. I keep forgetting to put this back up there. Okay, cosine of 90 minus x equals the sine of x. Now, I know that we have our cofunction identities at the top of our reference sheet. Okay, and you're like, well, okay, Mrs. Kopp, we could just use the cofunction identity. Yeah, you're absolutely right. If I encountered this in the middle of a bigger verification, I would use the cofunction identity. But today is more about just getting used to the idea of these sum and difference identities. So I want to take the time to practice a little bit with something that we know will be true. So cosine of 90 minus x. What I'm going to do first is go to my reference sheet and figure out which one of the formulas I should use. So I'm looking for the one that uses cosine, and it subtracts two angles. So I'm going to write this down on here as well. But what it says is this. It says the cosine of, and I'll put this back up on the screen in just a second. I'm just rewriting what's on here. Cosine of u minus v is the same as taking the cosine of u times the cosine of v and adding to it the sine of u plus the sine of v. So if you look at that formula, right, we've got the cosine of u minus v takes cosine of u times the cosine of v and adds to that the sine of u times the sine of v, not plus. So, you do remember it? Yeah. So in our example, we have 90 instead of u. So everywhere I see u, I'm going to replace it with 90. Kind of running out of room there. And then I have x instead of v. So everywhere I see a v, I'm going to replace it with x. So essentially what I'm saying is I can take this expression and replace it with all of this. Just plugging in the appropriate values. So replacing u and v with whatever I see in my problem. So what does that look like? Well, I'm going to take the left side and rewrite it, and I'm going to rewrite it as the cosine of 90 times the cosine of x plus the sine of 90 times the sine of x, and I'm trying to show that all of that is just going to be sine of x. Well, there are some things that because I have studied the unit circle, I should be able to calculate some of these values. So, and again, this is on your reference sheet if you need to look back at the unit circle. But what value is the cosine of 90 degrees? So go to 90 degrees and find the cosine, which is the x value. What is the cosine of 90 degrees? It's 0. So that entire expression can be replaced with 0. And I will have 0 times whatever's left, which in this case is just cosine of x. I can do the same thing with the sine of 90. So I think about my unit circle, and I ask myself, what is the sine of 90?
Thank you.
You're welcome.
See ya. Bye, girl.
So what is the sine of 90? 1. So that entire expression gets replaced with just 1. And then I have 1 times the sine of x. Now it's a matter of doing a little bit more just evaluation. What is 0 times the cosine of x? It's 0. 0 times anything is just 0. And what is 1 times sine of x? Sine of x. So now I have it, don't I? 0 plus sine of x is just sine of x. And what I've shown is that these two things are the same. So I already knew that they should be the same based on my cofunction identities. Okay? But this is why. So this formula is how we would evaluate the sine or the cosine of two angles being added or subtracted from each other. So let's try a couple more. All right, so that one was just getting us comfortable with the formulas. Let's make it a little more interesting. Let's prove or show that the cosine of x plus pi over 6 is equal to 1/2 times, and then in parentheses, radical 3 times cosine of x minus sine of x. So I want to show that the left side of this expression is equal to the right side of this expression. So if we go back to our formula sheet, back to our reference sheet, we're looking now, and I'm sticking with cosine for now, I'm looking for where the cosine of two angles being added together is, because that's what I have on the left-hand side of this equation. I have cosine of x plus pi over 6. So it's still cosine, but now it's this expression. So now I've got to think about how do I rewrite what I have on my sheet. So instead of cosine of, I'm going to write this down here and I'll go back to my screen. Cosine of u plus v is the same as cosine of u times sine of u, times cosine of v, minus sine of u times sine of v. Okay, so we have this expression. Cosine of u plus v is the same as cosine of u times cosine of v minus sine of u times sine of v. And then we ask ourselves, what is going to replace u in our expression? What is going to replace v in our expression? So to replace u, I'm just going to use x. So everywhere I see u, I'm going to use an x. To replace v, I'm going to use pi over 6. So everywhere I see a v, I'm going to replace it with pi over 6. And then just like we did in the previous problem, right, I'm going to take this entire expression, I'm going to replace this guy with this whole expression. Replacing u and v with x and pi over 6. So let's do that. So I'm going to write cosine of x times cosine of v minus, not v, sorry, pi over 6. I forgot to make that replacement, didn't I? Minus sine of x times sine of pi over 6. And I want to show that that is 1/2 times the quantity of radical 3 cosine of x minus sine of x. Now again is when we're going to want to use our unit circle. Anytime you actually see an angle from your unit circle attached to one of your trig functions, that's a really big indication that we're going to have to use our unit circle values. So I'm going to look at my unit circle. I'm going to ask myself, what is the cosine of pi over 6? So go to pi over 6, square root of 3 over 2. Yeah, radical 3 over 2. That whole thing gets replaced with radical 3 over 2. Now we still have that cosine of x that we're multiplying by, right? This cosine of x just kind of follows along. Okay, minus, so I have sine of x that's just going to follow along. But then I ask myself, what is the sine of pi over 6? 1/2. And then I just rewrite what's on the right-hand side. And just in case you don't see, and this next step is not necessary, but I think it might help illuminate things a little bit better. Typically, when we write a number and a trig function multiplied together, we see the number out in front. So let me just rewrite this as radical 3 over 2 times the cosine of x instead of vice versa, minus 1/2 times the sine of x. And then let's take a look at what we have. And you could have done that all in one step. It didn't have to be 2 steps. Just trying not to throw too much at you at once. So compare the two sides. On the left side, I have radical 3 over 2 times cosine. On the right side, I see just radical 3 times cosine. On the left side, I see 1/2 sine of x. On the right side, I see just sine of x. But on the left side, I see this 1/2 being multiplied by everything here. So if I were to distribute this, would I get this? Mm-hmm. Yeah. So what's the opposite of distributing? What could I do? Instead of distributing the 1/2, if I want to make this side look like this side instead of the other way around, what would I do with the 1/2? You bring it outside, which is like, it's called factoring, right? So we're going to factor out the 1/2. Okay, and just in case you forget how this works, we would ask ourselves, if I were to multiply the 1/2 by something, I have to get radical 3 over 2 cosine. Well, the thing I would have to multiply by would be radical 3 times cosine. And then if I were to multiply 1/2 by something, I have to get negative 1/2 sine. Well, that would mean I'd have to multiply by negative sine of x. And then you've got the same thing on both sides. The key to this, especially in this example, was being able to properly use your unit circle. One thing that is a really common mistake, and I even said this morning and somebody still did it. Really common mistake that people make. So I'm going to talk about like when we evaluated this up here. Okay, so this is kind of an aside. Sine of pi over 6. What a lot of people will do is write sine times 1/2. The sine of pi over 6 is 1/2. So this is not how we would rewrite it. We just rewrite it as 1/2. We replace all of sine of pi over 6 with 1/2. Once you've used your unit circle, you no longer need to write the trig function that's associated with that angle. Okay, we've got one more today. This one is going to take a bit of space. I'm going to try to keep it on here since I want to record this. But just know you might need some additional space here. So sine of x plus y times sine of x minus y. And I want to show that that is equal to sine squared of x times cosine squared of y minus cosine squared of x times sine squared of y. This might look a little intimidating. But what we have is just two sum and difference formulas. Here's one of them, sine of x plus y. Here's the other one, just sine of x plus y. What I have to do is use my sum and difference formulas to rewrite each of those. So go to your reference sheet. This time we're using the sine of u plus v and the sine of u minus v. And we've got to replace all of our u's with x's, all of our v's with y's. So I'm not going to rewrite both those formulas on here. You can look at your reference sheet and find them. But what that's going to look like is this. That entire first expression that I've highlighted in the teal will be able to be replaced with sine of x times cosine of y plus cosine of x times sine of y. And this is right off of your reference sheet. I went straight from the reference sheet, and all I did was I changed u and v to x and y. That's it. That is all just that highlighted teal piece. I still have to figure out how to rewrite the highlighted yellow piece. Well, I do the same thing. Just instead of using sine of u plus v, I use sine of u minus v. And I rewrite it using that formula. So that's going to be sine of x cosine of y minus cosine of x sine of y. Now, I've run out of room, and this is not something that I would typically do. But instead of rewriting that whole expression, I'm just kind of drawing the arrow to show that it would be there. So what we're trying to show, we can't forget, we're aiming for that. Okay, let's just sort of focus in on what we have written for a minute. Sine of x times cosine of y, this guy right here, is exactly the same as this guy right here. So those two things are identical. And then if we look at the last terms in both set of parentheses, cosine of x sine of y and negative cosine of x sine of y, those are also exactly the same. So I'm going to kind of move off to the side here for a second. What we're really looking at is something that looks like this format. Two things that are identical. In between one set, I have a plus, and in between the other set, I have a minus. What is that? What do we call that when we have that kind of pattern? It's a special type of factoring. So what if we multiply it out? Let's multiply it out and see if we can figure out what it's called. So x times x would give me x squared minus xy plus xy minus y squared. What's going to happen with these middle terms? They're 0, right? So x squared minus y squared is what we end up with. What do we know about x squared minus y squared? Both perfect squares. Difference in between. What's that called? It's a difference of squares, right? So this entire thing is a difference of squares. We can recognize it either from this format, right? Either from the format where it is in its factored form, or we can recognize it, and I'm sorry, not from its factored form, from its multiplied out form, or we can recognize it from its factored form. The key here is that every single difference of squares, when we have it in factored form and then go to its unfactored form, the middle terms are going to always be 0. That's true for every time we see a difference of squares. So, using that, let's go back to what we've gotten written down here. I've got the same thing for both first terms. I've got the same thing for both last terms. This is basically a difference of squares, 1 plus and 1 minus. Why that's nice is that if we didn't realize that, we would have to FOIL this out and we would have this monster of an expression. But because I know it's a difference of squares, those middle terms are going to end up being 0. So all I've really got to worry about is what happens when I multiply the first terms together and the last terms together. That's all I care about, because those middle terms, when I multiply them out, are going to be 0. So let's look at that. when I multiply the first terms together, I have sine of x cosine of y squared minus, and then I have cosine of x sine of y squared. Again, I'm going to cheat just a little bit here. Now, one more little piece of like algebra trickery, I guess. It's not really trickery, it's just understanding what you're doing is no different than your algebra that you've done in years past. This sine of x times cosine of y squared, let's talk about how I could rewrite that. Okay, so what if I just had x times y squared?
X times x, y times y.
Right, x times y. That's what it means to square something. Now, if that's not clear, what we're doing is this, x times y times x times y. And then because we're multiplying, we can do that in any order, which means I could write it as x times x and y times y. And all of that just to say it ends up being x squared times y squared. Right? If we're multiplying two things together and we square them, it's the same thing as saying square those two things individually and then multiply them together. So I want to use that to rewrite what I have. So instead of saying sine of x cosine of y squared, I could say, well, let's square sine of x, and let's square cosine of y, and let's multiply those two things together. Those are equivalent expressions. And then we'll do the same thing with the second expression. So let's square cosine of x and square sine of y. And then we'll have the other way of writing it. Now, I'm going to rewrite what I have up top there because I think we've sort of lost track of what we're trying to do. And then what do you notice? They're the same thing. So it's not that this problem was, exceedingly difficult, right? It's just you've got to have really strong algebra skills, and you've got to know which formulas to use from your reference sheet. Okay, so the ones you do tonight are specifically going to have you practicing with the sum and difference formulas.